Welcome to GenAI Learner. Today we are going to deep dive into one of the most influential papers in the recent history of reinforcement learning for large language models. Before we begin, let me ask you a question. What do you think is the single most important algorithmic innovation that powered DeepSeek-R1's remarkable reasoning capabilities? Take a moment to think about it. The answer is GRPO, Group Relative Policy Optimization, and it was first introduced not in the R1 paper, but right here, in the DeepSeek-Math paper from February 2024. By the end of this lecture, you will understand exactly how GRPO works, why it is more efficient than PPO, and why it became the de facto standard for training reasoning models. Let us begin. Let me start with a question for you. How large a model do you think you need to match GPT-4 on mathematical reasoning? 540 billion parameters? 70 billion? What if I told you a 7 billion parameter model could get close? That is exactly what DeepSeek-Math achieved. The paper has two major contributions. First, they built a massive high-quality math dataset of 120 billion tokens from Common Crawl, using an iterative data selection pipeline. Second, and this is what we will focus on today, they introduced GRPO, a reinforcement learning algorithm that is both more memory efficient and more effective than standard PPO. What makes this paper historically significant is that GRPO became the backbone of DeepSeek-R1, which later demonstrated that pure RL training could produce emergent reasoning behaviors, the famous aha moment. So understanding GRPO is not just about this paper. It is about understanding the foundation of modern reasoning model training. This sets the stage for understanding the DeepSeek-Math pipeline itself. Before we dive into GRPO itself, let me give you the big picture of the DeepSeek-Math pipeline. Here is a question. If you wanted to build the best math reasoning model, what data would you use? Most people would say textbooks, ArcSiv papers, maybe curated datasets. But the DeepSeek-Math team found something surprising. Let me walk you through their three-stage pipeline. First, pre-training. They built a 120 billion token math corpus from Common Crawl, that is, the raw web, using an iterative classifier. They started with Open Web Math as seed data, trained a fast text classifier, mined more data, had humans annotate it, and repeated this 4 times. Second, supervised fine-tuning with 776K examples. Third, and this is our focus, reinforcement learning with GRPO using only about 144K questions. Now here is the surprising finding. They discovered that code training before math training actually improves mathematical reasoning, and that ArcSiv papers, which everyone includes in math training, were essentially ineffective. This challenges a lot of conventional wisdom. Now, let us look at the remarkable results this pipeline achieved. Now let me show you why this paper got so much attention. Look at these numbers. A question for you. What was the state-of-the-art for open-source models on the math benchmark before DeepSeek-Math? It was around 35% for models like Lemma 34b and QN 72b. DeepSeek-Math RL 7b, a model 7 times smaller, achieved 51.7%. That is a massive leap. And look at the progression. The base model gets 36.2%. After SFT, it jumps to 46.8%. And after GRPO, it reaches 51.7%. That last 5 percentage points from RL is particularly impressive because it comes from training on only about 144K questions, a tiny fraction of the SFT data. Even more remarkable, the RL training improved out-of-domain performance too. Chinese math benchmarks improved from 84.6% to 88.8%, even though the RL training only used English data. This tells us something profound about what RL is doing to the model. This incredible performance was only possible because GRPO solved a critical problem with traditional PPO. Now let us get into the heart of the matter. Before we understand GRPO, we need to understand what problem it solves. So let me ask you, in standard PPO for LLM training, how many models do you need to keep in memory simultaneously? Think about it. The answer is 4. You need the policy model, that is the LLM you are training. You need a reference model, a frozen copy of the SFT model to compute KL divergence so the policy does not drift too far. You need a reward model to score the outputs. And you need a value model, also called the critic, which estimates a baseline for computing advantages. Now here is the problem. The value model is typically the same size as the policy model. So if your policy is a 7B model, you need another 7B model just for the critic. That is a huge memory burden. And there is another issue. In the LLM setting, the reward model typically only gives a single score at the end of the entire output. but GAE needs per-token value estimates. Training an accurate per-token value function when you only have a single end-of-sequence reward is really hard. This is the motivation for GRPO. Let us now look at the math. This is the PPO objective, equation 1 from the paper. Do not be intimidated. Let us break it down piece by piece. The core idea is simple. We want to increase the probability of tokens that lead to good outcomes and decrease the probability of tokens that lead to bad outcomes. The ratio pi_theta over pi_theta_old tells us how much the new policy differs from the old policy for each token. If this ratio is greater than 1, the new policy assigns higher probability to that token. The advantage A_t tells us whether that token was good or bad. If A_t is positive, we want to increase the ratio. If negative, decrease it. The clip function is the key PPO innovation. It prevents the ratio from going beyond 1 plus or minus epsilon, so the policy cannot change too dramatically in one step. Now, the reward at each token, equation 2, includes a KL penalty. This is the log ratio of the current policy to the reference model, weighted by beta. This prevents the policy from drifting too far from the original SFT model. The critical question is, how do we compute A_t? In PPO, we use GAE with a learned value function, and that value function is the expensive part. Now we arrive at the key innovation. Let me ask you this. If the value model in PPO is expensive and hard to train accurately, what is a simpler way to estimate whether an output is good or bad? Pause and think about it. Here is the insight. Instead of asking, how good is this output in absolute terms, which requires a value function, we can ask, how good is this output compared to other outputs for the same question? That is the core idea of GRPO. For each question, we generate not one but G outputs. In the paper they use G equals 64. We score all of them with the reward model. Then we normalize the rewards within the group by subtracting the mean and dividing by the standard deviation. Outputs that scored above average get positive advantages. Those below average get negative advantages. This is beautifully simple. No value model needed. No GAE computation. Just sample, score, normalize. And notice something elegant. This group relative comparison aligns perfectly with how reward models are trained in the first place. They are trained on comparisons between outputs for the same question. So how do we actually calculate these advantages in GRPO? Let us use a simple example. Imagine I ask you, what is 2 plus 3? And I get 5 responses. Let us say the rewards are 1, 0, 1, 0, 1. What is the average reward here? It is 0.6. Now, if we normalize these rewards by subtracting the mean and dividing by the standard deviation, the correct answers, with a reward of 1, would get a positive advantage of plus 0.82. The incorrect answers, with a reward of 0, would get a negative advantage of minus 1.22. This is the power of group relative advantages. We are not trying to learn an absolute value for each token. We are simply saying, compared to other responses to the same question, was this token part of a better or worse answer? This makes the advantage calculation much more robust and efficient. This is a fundamental difference from PPO, where we need a separate value function to estimate these advantages. Now that we understand how advantages are computed, let us look at the full GRPO objective. Let us now look at the full GRPO objective. Equation 3 from the paper. Compare it to the PPO objective we saw earlier. What are the differences? First, notice the outer summation. We are averaging over G outputs in the group, not just one output. Second, the advantage underscore IT, notice the hat, is computed from group relative rewards, not from GAE. Third, and this is subtle but important, the KL divergence term is added directly to the loss function, not to the reward. Why does this matter? In PPO, the KL penalty is baked into the reward, which then feeds into GAE to compute advantages. This means the advantage calculation is entangled with the KL penalty. In GRPO, the advantage is purely based on reward comparisons, and the KL penalty is a separate regularization term. This is cleaner and simpler. The KL estimator in equation 4 is also worth noting. It uses an unbiased estimator that is guaranteed to be non-negative, which is a nice mathematical property. Now, let us get to the core of reinforcement learning. What is the fundamental principle that drives the model's learning? It is the product of probability and advantage. The gradient of the policy is proportional to the probability of an action multiplied by its advantage. So what happens in these 4 scenarios? First, if you have a high probability token with a positive advantage, what should the model do? It should increase that probability even more. Second, if you have a low probability token with a positive advantage, the model should increase its probability. Third, if you have a high probability token with a negative advantage, the model should decrease its probability. And finally, if you have a low probability token with a negative advantage, the model should decrease its probability even further. This simple yet powerful mechanism is how the gradient pushes the model to generate more of what is good and less of what is bad. This is the essence of how GRPO and RL in general learns. Let us revisit the PPO objective and specifically the clipping mechanism. Why do we need to clip the probability ratio? Think about it. The clipping mechanism is crucial for stability. It prevents the new policy from deviating too much from the old policy in a single update step. Imagine you have a token with a very high positive advantage. Without clipping, the policy might drastically increase the probability of that token, leading to unstable training. The clip function ensures that the ratio of the new policy's probability to the old policy's probability stays within a small range, typically 1 plus or minus epsilon. So if the advantage is positive and the ratio is already above 1 plus epsilon, we stop increasing the probability. If the advantage is negative and the ratio is below 1 epsilon, we stop decreasing it. This controlled update is what makes PPO and by extension GRPO stable. This clipping mechanism is a core part of how we manage policy updates in GRPO as well. Now let me ask you a question about reward granularity. If a student writes a 10-step math proof and gets the final answer wrong, should we penalize every step equally? Or should we try to identify which steps were correct and which went wrong? This is the difference between outcome supervision and process supervision. In outcome supervision, we give a single reward at the end, correct or incorrect, and every token in the output gets the same advantage. It is simple but coarse. In process supervision, we use a process reward model that scores each reasoning step. The advantage of each token is then the sum of normalized rewards from all subsequent steps. Think of it like this. If step 3 was correct but step 7 was wrong, process supervision can reinforce step 3 while penalizing step 7. The paper shows that GRPO with process supervision outperforms GRPO with outcome supervision, which makes intuitive sense. Finer-grained feedback leads to better learning. Let us now look at the complete algorithm. Algorithm 1 from the paper describes iterative GRPO. Here is a question. Why would you need to iterate? Why not just run GRPO once? Think about it. The answer is that as your policy model improves, the reward model that was trained on outputs from the original SFT model may no longer be accurate enough to evaluate the improved policy's outputs. So in iterative GRPO, after each iteration, they generate new training data from the improved policy, update the reward model, and continue training. The key hyperparameters are group size G equals 64, KL coefficient beta equals 0.04, learning rate 1E6, and they do a single policy update per exploration stage. Notice the replay mechanism for the reward model. They keep 10% historical data when updating it, which prevents catastrophic forgetting. The paper shows that iterative RL brings significant improvements, especially in the first iteration. This is one of the most insightful parts of the paper. Let me ask you, what do SFT, RFT, DPO, PPO, and GRPO all have in common? At first glance, they seem like completely different algorithms, but the authors show that they all share the same gradient structure, equation 5. Every method computes a gradient that is a weighted sum of log probability gradients. The only differences are in 3 components. Where does the data come from? How do we compute rewards? And what is the gradient coefficient? Look at Table 10. SFT uses human-selected data with a gradient coefficient of 1. It equally reinforces every token. RFT uses a binary coefficient, 1 for correct outputs, 0 for incorrect. It cannot distinguish between a barely correct answer and a brilliant one. GRPO uses a continuous coefficient based on normalized group rewards. It can differentially reinforce outputs based on their quality. And crucially, GRPO also penalizes bad outputs with negative coefficients, while RFT simply ignores them. This unified view makes it clear why GRPO is more powerful. Now let us look at the experimental evidence. Figure 5 from the paper shows the training curves of 4 methods on GSM-8K and math. Before I reveal the results, let me ask you to predict the ranking. We have RFT, offline, binary rewards. Online RFT, online, binary rewards. GRPO with outcome supervision, online, continuous rewards, single reward per output, and GRPO with process supervision, online, continuous rewards, per step rewards. What order would you expect? The results confirm our theoretical analysis perfectly. GRPO plus PS is the clear winner on both benchmarks. Notice something interesting about the early training. Online RFT and RFT start at similar levels, but online RFT pulls ahead later. This makes sense. Early on, the policy is similar to the SFT model, so online and offline sampling give similar data. But as training progresses, the policy diverges, and real-time sampling becomes increasingly valuable. GRPO beats online RFT because it can differentially weight responses, not just accept or reject, but reinforce proportionally to quality. We just saw how GRPO outperforms other methods, but can we push it further? Here is another important question. Once you have trained your model with GRPO, can you just keep training longer to get better results? Or do you need to do something else? Look at Figure 6. The purple line is iteration -0, the initial GRPO training. It improves and then plateaus. But when they update the reward model using the improved policy's outputs and start iteration -1, the orange line, performance jumps significantly. Why? Because the original reward model was trained on outputs from the SFT model. As the policy improves, it generates outputs that are qualitatively different from what the reward model was trained on. The reward model's evaluations become less reliable. By updating the reward model, you get better training signal, which leads to further improvement. Iteration 2 shows diminishing returns, suggesting that 2 rounds of iteration capture most of the gains. This iterative approach is crucial for sustained progress. Now, let us dive into a more fundamental question about why RL works at all. This is perhaps the most profound finding in the paper, and it has deep implications for how we think about RL for LLMs. Let me pose this question. Does reinforcement learning teach the model new mathematical knowledge, or does it do something else? Look at Figure 7 carefully. The blue and red lines show pass at K, the probability that at least one of K samples is correct. Notice that the Instruct and RL models have nearly identical pass at K curves. This means the RL model cannot solve any problems that the SFT model could not already solve with enough samples. Now look at MAJ at K, majority voting accuracy. Here, the RL model dramatically outperforms the SFT model. What does this tell us? RL does not expand the model's capabilities. Instead, it makes the model more reliable. It takes correct answers that were rare in the SFT model's output distribution and makes them more frequent. It is like a student who knows the material but sometimes makes careless mistakes. RL teaches the model to be more careful and consistent. This insight is fundamental for understanding what RL can and cannot do. We will now move on to the practical details of GRPO training. We have seen the theoretical underpinnings and the impact of GRPO. Now let us talk about the practical details, because if you want to implement GRPO, these matter. A question: how many outputs do you think they sample per question? The answer is 64. That is a lot of outputs, and it means the sampling phase is computationally expensive. But here is the trade-off. You save the entire cost of training and running a value model. The learning rate is very small, 1e6, because you want stable updates. The KL coefficient is 0.04, which provides moderate regularization. An important detail: they only do a single policy update per exploration stage. This means after sampling 64 outputs and computing advantages, they update the policy once and then resample. This is conservative but stable. And notice the training data. Only about 144K questions, all from GSM-8K and math. Despite this limited scope, the improvements generalize to Chinese math benchmarks and other out-of-domain tasks. This suggests that RL is learning something general about mathematical reasoning, not just memorizing specific problem types. Now let us look at the future directions for GRPO. We have explored GRPO's mechanics, its impact, and its practicalities. Let me conclude with a forward-looking question. If GRPO improves MAJ at K but not pass at K, what would it take to actually expand the model's fundamental capabilities through RL? The paper suggests 3 directions. First, better data sources. Instead of just using SFT questions, explore out-of-distribution prompts and advanced sampling strategies like tree search. Second, more robust algorithms. The current approach fully trusts the reward signal, but reward models are imperfect. We need RL algorithms that are robust to noisy rewards. Third, Better reward models, especially process reward models that can provide fine-grained feedback on each reasoning step. Looking back from 2026, we can see that many of these directions were pursued. DeepSeek R1 showed that GRPO could enable emergent reasoning behaviors. The model learned to think step by step, verify its own work, and even have aha moments, all without supervised fine-tuning. GRPO and its variants like DAPO have become the standard approach for training reasoning models. The key takeaway: GRPO is not just an algorithm. It represents a paradigm shift in how we think about training LLMs to reason. Thank you. Any questions?